All right, Honors Chem. Today we are going to talk about these electrons now and see how they interact in these different levels that they thought that atoms have. They used to think of the atoms as having kind of a planetary model where we had orbits around the nucleus. We now know that that's not true. We've done quantum mechanics, and you already know that instead of orbits, we have shells, and we have subshells. We have the s orbitals, we have the p orbitals, we have the d orbitals, we have the f orbitals, all in different levels due to the row that it is in the periodic table. Okay, so here we go. This is Niels Bohr, and he was a German physicist. Actually, he was Danish. That's wrong. He was Danish. And a little side note, he had such terrible handwriting that his doctoral dissertation was actually written by his mother so that people could read it. So he dictated it and she wrote it down because no one could read his writing. Kind of funny story. All right, so in his attempt to explain the hydrogen spectrum, Bohr developed his planetary model of the atom. Bohr used the quantum theory, a theory of energy and emission that had been stated by German physicist Max Planck. And by the way, Max Planck is a huge science institution in Göttingen, Germany, that has some of the world's premier science going on there. Absolutely amazing institution. Planck assumed that energy, instead of being given off continuously as like a continual line, was actually given off in quanta, or little groups. Okay? Quanta of radiant energy were often called photons, and we think of photons as visible light that we can see. He further stated that the amount of energy given off is directly related to the frequency of light emitted. This is the relationship. The energy is directly related to the frequency. Remember, nu is frequency. Now that alpha in there just means directionally proportional. Replacing that alpha sign with an equal sign means that we need to actually put some kind of a constant in there. Okay, so we need a proportionality constant. So we do now have that proportionality constant where energy is equal to h, which is Planck's constant, times the frequency. Okay? Now Planck's constant is equal to 6.6262 times 10 to the negative 34, super small number, joules times second divided by photon. So this is per photon. Now, I have hammered units a lot this year, and joules is probably something that you are going to get introduced to a lot in physics. Joules is a measure of energy or a measure of work. So let's just break down joules. So joules is what we call a Newton meter. So Newton is just a kilogram under the Earth's influence. So Newton is a kilogram per meter second squared. So the kilogram per second squared is just the Earth's gravitational pull. So that's what a joule really in scientific, the base units becomes. Kilogram meter per second squared. Okay, so let's look at this. We have this relationship where our energy is equal to Planck's constant multiplied by the frequency. What if we want to use wavelength? And we don't have the frequency, but we have the wavelength. Can we rearrange this using this relationship? Yeah, so if I rearrange this relationship, then V is equal to C divided by the wavelength, or lambda. So if I'm substituting this for that, right? So here we go. So E is going to be equal to H times the speed of light divided by lambda. So if we want to isolate lambda, or the wavelength is equal to Planck's constant times the speed of light, all divided by the energy of that photon. Okay, so here we derive various ways that we can use this equation by putting both of those equations together. So we can use the frequency or the wavelength and get what we need to. Okay, so notice also, let's do a little analogy here. If you've ever been to the ocean and you've been in nice, gentle waves that are far apart, you're standing there, right, in the waves, you don't have a whole lot of difficulty standing up and staying standing up. But if you are in a rough ocean where you have a bunch of waves coming at you really, really fast, really, the frequency is really, really high, those waves have a lot more energy than the green waves. Okay? So notice that as frequency increases, notice our wavelength here went really far down compared to our green waves, right? Our wavelength decreases and the energy increases. Okay, so we could also map this out by doing a couple different diagrams, Cartesian diagrams. If I have wavelength and frequency, they're inversely proportional to each other. So it would look like that. I would have an inverse relationship. If I do wavelength and energy, as wavelength gets bigger, energy gets smaller. So it's going to look like that. If I do the frequency and energy, as the frequency goes up, the energy goes up. Okay? So those are different ways of looking at those relationships. Okay? So here we go. What is the energy of a photon of red light with a frequency of 4.48 times 10 to the 14th hertz? Now remember, hertz is just number of cycles per second, okay? Or just per second, okay? So we have this equation right here that we're going to use. Our energy is equal to Planck's constant multiplied by that frequency, which we have here, okay? We're going to substitute Planck's constant, and let me highlight Planck's constant again really quick, because that is a number that you are going to want to be familiar with right here. So 6.6262 times 10 to the negative 34. Okay, so here we go. Let me get a pen again. So I have Planck's constant, 6.6262 times 10 to the negative 34, and that this is joules per second, or joules times second per photon. And we are going to multiply this by our frequency, which is 4.48 times 10 to the 14th. And remember, hertz is per second. So this is going to cancel the seconds out. That leaves us with joules per photon. Okay, so energy per photon is how we're going to read that. Okay, so when we multiply that out, we get an energy of 2.97, and there goes my computer. And it won't let me. So we get 2.97 times 10 to the negative 19 joules per photon. Okay. So hopefully this won't take too long. I'm going to grab my calculator. I think it's way the heck over here. A pile of books Okay, so we get 2.97 times 10 to the negative 19th joules per photon on this because the seconds cancel out. Okay, notice the amount of energy that we get off of these is really, really small. And we would expect that because photons are super, super small. Okay. All right. Atomic emission spectra. We're going to talk about this a little bit for the next couple of days. Bohr pointed out that the absorption of light by hydrogen at definite wavelengths correspond to definite changes, right? Wavelengths definitely have definite energy signatures. And so if I have emissions from hydrogen, that means that these electrons are definitely jumping very specific amounts because I always get the same colors when hydrogen has the emissions. Okay? He reasoned that these very specific energies came from orbits of the electrons surrounding the nucleus being very specific in their diameter. Okay? Furthermore, electrons could occupy only certain orbits because we only got certain colors. We didn't get the whole spectrum. We only got certain colors. So certain orbits were going to be there. Only orbits allowed were whose difference in energy equaled the energy absorbed when the atom was excited. Bohr pictured the hydrogen atom as an electron circling a nucleus at a distance of about 53 picometers. He also imagined that this electron could absorb a quantum of energy and move to the next larger orbit. When that electron drops back down to the original orbit, energy emitted would be the spectra that he saw in the visible light. The energy of this photon would be exactly the same energy difference between the two orbitals. So I'm going to put a video demo of this together for you and put it in the Canvas notes as well. Okay, it's really cool and you'll see what I mean. It's one of my favorite demos to do. Okay, so this is what Bohr was envisioning. We would take an electron, and I'm going to make it pink, starting out in the hydrogen atom. And if I excited that electron in some way, gave it some energy, heated it up, put some electricity through it or whatever, gave it some more energy, we could get that electron to move up to a larger orbit. Or maybe if we gave it a lot of energy, we could get it to really move up to yet a higher orbit or a higher energy level. Now that electron can't stay there forever because guess what? Nature likes to, that's right, go to a lower energy state. Go to the lowest energy state possible, always. So eventually, that electron would fall back down, okay? And as it would fall back down, we would get some energy off of here. We would get some kind of a wave. And sometimes that energy would be a wave that actually was visible in the visible light spectrum. Or maybe it would fall all the way back down and give yet a different type of wave. Or just here, it would fall down and give a different wave. So, Bohr thought of these orbits of the electrons kind of like when you're climbing up a staircase, right? When you're climbing up a staircase, you're going from one step to the next. You can't magically float here in the middle of two steps. Yeah, you could have one foot on one step and one foot on the other, but your weight is going to be on one foot or the other. Okay, you're not magically floating in between both steps. So we envisioned these electrons going up what we call quanta or chunks of energy and then falling back down with these very specific energy distances that we can get wavelengths of visible light and measure. Okay? So this is what we see when we look at the spectrum of hydrogen. This is the spectrum of hydrogen. We get a dark blue line, a light blue line, and another light blue line, a green line, a pretty wide yellow line and a pretty wide red line. We always get these spectra when we look at hydrogen, okay? Every single time. We don't get the whole rainbow because we have very specific wavelengths that are coming off, which mean we have very specific energies that are coming off, okay? So we can do this with every single element as well. Every single element has their very own unique spectrum of energy lines that come off of it. And we indeed can tell what element it is based on the spectral lines that we get coming off of that element. This is how we ID the elements in the stars and ID the elements in the nebula in the universe, because we can filter out those spectral lines and we can tell what elements are in those clouds and in those stars. Okay, so here we go. So ground state, we will have that electron in that ground state, and we will excite it. And as it is excited like this, it eventually falls back down and gives us off a wave. And sometimes that wave is part of that visible spectrum. Okay? So this is the series that Bohr thought of for the hydrogen. Okay? This is the energy series. So there's the Lyman series for the ultraviolet spectra that we can get off. There's the infrared series that we get off of hydrogens. And then there's the visible series, which is the Balmer series. Okay, and the different lines from the blue, red, and purple are outlined there in what they thought was happening with the orbitals or the orbits in that hydrogen. Notice the red line, because it has the lowest energy, is just the first jump. The lighter blue is the second jump. The darker blue, because even more energy, is the third jump. And that violet, because it's even more energy, is even higher. Okay? So here we go. Bohr's model explained hydrogen's observed spectral lines. However, the model failed to explain the spectral lines of any other element. So it worked really good for hydrogen, but not so much for anything else. So that's where this model falls apart. It's useful in that we know that electrons can be excited, and we know that they get excited and go to a higher energy, and that they come down, and we have very specific energy jumps for very specific elements, and we can ID elements based off of their spectral lines, but they're not orbits. They're not planetary model orbits, okay? So we had to rethink our model after this, okay? So the movements of electrons and atoms are not completely understood even now, even to this day, okay? However, substantial evidence indicates that electrons do not move around the nucleus in circular orbits. We have our quantum mechanics. We have our S orbit, our P, our D, and our F. Okay? So we have now our other scientists coming in and talking about electron clouds, which is our current model. We have Louis de Broglie from France. Frequencies predicted by Bohr for the hydrogen spectrum are essentially correct, but not exactly. Improved instrumentation has shown that hydrogen spectral lines predicted by Bohr models are actually several lines that are very, very closely spaced together. To account for this, the atomic theory again had to be refined. De Broglie used Planck's ideas concerning radiation and had the idea of discrete amounts called quanta once again. This theory seemed to give waves the properties of particles. We have thought about the electron as particle up until now. De Broglie flipped this. What if Planck was correct and the electron was actually a wave instead of a particle? Okay. Scientists found by experiment that in some ways the electron stream acted the same way as a stream of light, like a wave. Furthermore, wavelength electrons was exactly what de Broglie predicted. So that begs the question then. Electrons actually do have a little bit of mass. So little that we essentially consider it zero. But when we're doing nuclear chemistry and we're doing mass defect, we actually have to take that into account. So if it's a wave, but it has mass, what really is an electron? So the thing that we really have to think of is the electron a wave, or is the electron a particle? And my answer is yes, both. It has wave-like properties and particle-like properties, so it is a particle that probably functions as a wave and travels as a wave. And so that's really how we think of the electron right now. Okay, so we are going to call it good here, and I will upload those videos and have a great evening. We'll talk to you later. Bye.